All right, welcome to the explainer. We're swimming in these invisible fields of force and energy all the time. So today, we're going to make them visible. We're going to break down exactly how electric charges create these fields and, maybe more importantly, how they store energy inside them.
Okay, so here's the game plan. First, we're going to map out the electric fields around some simple shapes. Think spheres, rings, that kind of thing. Then, and this is the really cool part, we'll connect those fields to this super powerful concept, potential energy. We'll even see how you can calculate the energy stored in pretty much any system of charges.
First up, let's tackle the most basic 3D shape you can think of, a solid sphere. But not just any sphere. This one is non-conducting, and it's got an electric charge spread perfectly, evenly, all the way through its volume.
Now, before we can really dig in, we need to get one key concept down, volume charge density. It's got that Greek letter rho. Honestly, just think of it like the density of electricity. It's just a number that tells you how much charge is crammed into a certain amount of space. Super simple, right?
So how does this electric field actually behave? Well, this is where it gets interesting. It turns out there are two completely different sets of rules. It all depends on where you are. There's one rule for when you're inside the sphere and a totally different one for when you're outside.
And here's the part that might mess with your head a little. When you're inside the sphere, the electric field actually gets stronger the farther you move from the center toward the edge. But the second you pop outside that surface, everything changes. The rules flip. The whole sphere suddenly starts acting like all its charge is crushed down to a single tiny point right at its center. And from there, the field just gets weaker and weaker the farther away you go.
This graph right here, it tells the whole story perfectly. Look, on the vertical axis, you've got the field strength, and on the horizontal, that's your distance from the center. You can see it clear as day. The field climbs in a straight line, nice and linear, right up to the sphere's surface. That's at distance A. That's the peak. And then, boom, it starts to fall off, following that classic inverse square law. You double the distance, the field strength drops to a quarter. Classic.
Okay, let's switch things up. We've done the 3D sphere. What if we basically squash it? Let's see what happens when we flatten that charge into a simple, one-dimensional ring. The electric field from a charged ring, but only along its central axis, well, it's pretty fascinating. You can see the formula there. It depends on the total charge, the ring's radius, and your distance x from the center. But the really interesting part, the part I want you to focus on, is what happens when that x is 0. What happens when you're standing right in the dead center?
Yeah, right in the exact center, the electric field is 0. Nothing. Zilch. Think about it. If you put a tiny little test charge right there, it wouldn't move at all. It's like a perfect 360-degree tug-of-war. The force from every single piece of the ring is pulling on it equally from all sides, and it all just cancels out. A perfect stalemate.
And this graph just shows that beautiful symmetry in action. See, the field is 0 right at the center, just like we said. Then, as you move away from the center along the axis, it gets stronger and stronger, hits a maximum, and then, just like our sphere, it starts to fade away, getting weaker the farther out you go.
Okay, so now that we've got the full ring down, we can generalize. We can take this idea and apply it to just a piece of a circle, an arc. And believe it or not, we can even stretch that logic to figure out the field from something totally different, like a straight wire. So there's a general formula for any arc of charge. And once you have that, you can find the field for all sorts of specific shapes. Easy. Got a semicircle? Just pop in 180 degrees. A 90-degree quadrant? Plug in 90. The underlying principle is exactly the same. And we can push this idea even further. We can actually use it to calculate the field from something that seems completely unrelated, like a long straight wire. The whole trick is just to break down the electric field into its up and down and left and right components. Add all those little pieces up, and you can find the total field at any point you want.
Okay, let's pause. We've spent all this time mapping out these electric fields. But here's the thing. These fields aren't just invisible forces pushing and pulling. They also store energy. And to get a handle on that, we need to kind of shift our thinking. We've been talking about the electric field, which is a vector. It has strength and direction. Now we need to think about electric potential energy. That's a scalar. It's way simpler. It's just a number, a single number that tells you how much energy is stored up.
So this brings us to a really fundamental question. How much energy is actually stored in a system of charges, just by having them sit near each other? Where does that energy come from?
Well, the whole idea comes from figuring out how much work it takes to build the system in the first place. Imagine you have a couple of charges infinitely far apart. Now you start pushing one of them closer to the other. The work you have to do, fighting against that electric force, it doesn't just disappear. It gets stored in the system as potential energy. It's just like when you compress a spring, you're storing energy in it. And here is the absolute best part. All of that calculus, all that math about work and integrals, it all boils down to this one incredibly simple and powerful equation. The potential energy is just a constant, K, times the two charges divided by the distance between them. That's it. So elegant.
All right, theory is great, but let's make this real. Let's see how we actually apply this formula. We're going to run through a couple of different setups just to show you how easy it is to calculate the energy stored in a system.
So here's our first case, a positive charge and a negative charge. We plug the numbers into our formula and look what we get, a negative potential energy, minus 2.7 joules. So what does a negative energy even mean? It means the system actually released energy when these two charges came together. And that makes perfect sense, right? Opposite charges attract, so they want to get closer. The system does the work for you.
Okay, but what happens when you have more than two charges, like 3 in a line? The principle is super simple. You just calculate the potential energy for every possible pair of charges. So you do the first and second, then the second and third, and don't forget the first and the third. You calculate the energy for each pair, and then you just add them all up. That's your total.
And you know what? It doesn't matter what the shape is. The exact same principle applies. Here we've got 3 charges in a triangle. So what do? We find the energy for each of the 3 pairs, the 3 sides of the triangle, and you guessed it, we just add those 3 numbers together.
So this brings us to a final thought to chew on. If bringing opposite charges together releases energy, what does that tell us about pulling them apart? You have to fight their attraction, right? You have to put energy into the system. And that energy you add, it doesn't just vanish. It gets stored right there in that invisible field between them. And that, right there, is the fundamental secret of potential energy.